Hello. Today's lecture is on the nature of sound. And this can be a little bit of a complicated topic. And so you may even want to listen to this again. Definitely pays off to hear some things more than once. Be sure you supplement this with the information from your textbook, which I've put up which chapter you need to refer to there as well. I have websites and some video embedded in this PowerPoint, and hoping that the Panopto will capture those videos as I present them for you. So here we go, the nature of sound. So how is sound created is the biggest question. We take it for granted that sound is out there, but it has to be created. What do you need to create sound? Well, you need a medium. So a medium that us humans are used to hearing sound in is through a gas. But there's other mediums. There's solids and liquids that sound can be created in as well. So we have a medium, okay, but then we still maybe don't have sound unless we put that medium into vibration, unless we disturb that medium. So we have to have a medium, and we have to force it into vibration. We have to disturb the medium. So mediums are made up of particles that, depending on which medium, how close those particles are. So for sound, we also need what we call an elastic medium. This simply means that the particles need to be able to interact with each other. Basically, they bump into each other. So what is an elastic medium? Here's the actual definition you may find helpful. So an elastic medium is defined by its resistance to change, which might seem a little counterintuitive to the word elastic. But when we put the next phrase in there, it might make a little more sense. So it doesn't want to change, but when we do get it to change, it wants to return back to its original form. So it takes a lot to get it to change, but it's always working to get back to its original form if it is changed. So with that definition, what do you think is the more elastic medium? A solid or a liquid? So which of these mediums, a solid or a liquid, doesn't want to change? A solid. Okay. Solids don't want to change. So they have the greater elastic medium when we compare it to a liquid. Okay, so how about a liquid or a gas? Do you think a liquid wants to stay the same, greater than a gas, or the other way around? Well, a liquid wants to stay the same. A gas is actually the least elastic. Okay, it doesn't take a lot to get it to change. So it is the least elastic medium over a liquid or a solid. And you're going to see why this becomes important soon. So let's move on to waves. So a wave, so we're going to kind of leap ahead why I'm talking about a wave. You've heard of the term sound wave. So that's kind of what I'm building up to here. So a wave is defined by how the particles move through a medium relative to the direction that energy moves. Okay, so a medium has particles in it. We're going to disturb them. When we disturb them, we create energy that moves through the medium. But what do the particles themselves do? Okay, they can move in directions. There's two basic directions I'm going to talk about that the particles can move in. And they can move in a transverse direction or a longitudinal direction. And I'm going to use a little video link to demonstrate these. So in general, energy, that energy from that original disturbance that placed our medium, that disturbed our medium, is going to get carried through it. It took energy to disturb that medium. That energy from that disturbance is going to move through our medium. A fancy term for that, which I would like you to learn, is the term propagated. So the energy is going to go transverse, and that means that the particles are actually perpendicular to the motion of the energy. So if you do not understand the word perpendicular, you need to look it up. If you do not understand a word that I do not define it, please look it up so you have more complete. I'm not that familiar with your vocabulary, and so you need to help yourself learn this material as well by looking up terms that you are unfamiliar with. Longitudinally. So this is when the particles, or matter, those are all interchangeable. Molecules, matter, particles, those are all interchangeable. And that's that mass, really, that is making up the medium. Alright, so energy is going to flow through the medium. What do the particles do? If they are moving in the same direction, or basically parallel to that energy, that's longitudinally. And here's the kicker, is this is what sound does. Sound travels longitudinally through a medium. Alright, I'm hoping that Panopto captures this, because this is really cool. Alright, so these two are the ones I'm talking about. So this is a transverse wave. So what you do is you can look at this, kind of focus your eyes two different ways. So you can see a wave is created. Energy is going through from here, from the beginning to the end. But these little black dots represent the particles. What are they doing? They're going up and down. So they are moving perpendicular to the energy that's going through the wave. So that definition, remember, is of a transverse wave. Okay, that's just nice to know. And sound, though, travels on longitudinal waves. So now, look at this. This is great. Look at this. Two ways, like I said, you kind of almost have to refocus your eyes. So you can see that energy is getting from this beginning point of the wave to the end point. Energy is going through that. You can see that in both of these examples. Now, what they've done here is pointed out. So see, they've got that the wave is traveling through, okay? But look at what the particle is, the little red guys that they were pointing out here. Those are the particles. These are all the particles in the medium. All these little black dots are the particles. They've just highlighted a couple and turned them red, so you make them easier to follow. But you can follow one of them up here too. It's not that hard. See this little guy? He's just going back and forth. We say he's oscillating. But the energy is being propagated, you've learned that term now, through the wave. It's being carried through. Okay, so you can see that the particle is moving parallel to the wave. And so that is the definition of a longitudinal wave, and that's where we're going to continue talking, because that is the way sound is carried, is on a longitudinal wave. This is important. Did you note that in both cases, whether it's longitudinal or transverse, no particle of the medium itself actually moved very far, did it? Okay, you need to remember this and kind of think about this and go back to that wave demonstration and look at it again with this fact, that no particle of the medium actually moves very far. Look, you saw those little red dots, you saw the little black dots that were the particles, the molecules of the medium. They just kind of boink, 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 boink. They didn't go very far, right? They spent their whole life, quote unquote, just bouncing boink, 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 where the energy went from the beginning and all the way through to the end. Okay, here's another way to look at it. So another way to watch this is by looking at the energy that goes through the slinky, and then watch it again, watching the individual kind of rings of the slinky, and you will see what I'm talking about as well. Let's see. I should be able to get... It doesn't want to play. It did. Rats. Not sure how to fix this, but I will put the actual, link in Canvas, so you can watch this demonstration over and over and over again if you happen to want to. But I highly recommend that you watch this. Sorry, it's not working for this demonstration, but go out and watch it within Canvas. It'll be there. Okay, we're adding some more information. So we have our elastic medium. We have to have an elastic medium. There's another property that we have to have, and that is called inertia. Okay, the term inertia now. So, elasticity, the more displaced the particles are, the more they want to return. We said that. It takes a lot to get them to be displaced, but then with that same amount, they want to come return. But we have inertia. Definition of inertia is the tendency of the particles to remain in motion. Okay, so these are two different properties that you will see actually work together to get that energy to propagate through that wave. They work together. On the next slide, there's a very good figure that demonstrates this. Then I'm going to add one more term, and that's damping, and that's friction. So if we didn't introduce damping, waves would just continue on forever and ever and ever. Okay, but we have friction in a medium, and that will eventually slow down elasticity and inertia, causing those molecules that were originally displaced from that disturbance to come back to rest. Okay, so here's the figure I'm talking about. So elasticity, inertia, and damping all work together to create this simple harmonic motion over time. Okay, so putting these all together creates what we call simple harmonic motion of the particle in a wave. So here's our little particle guy. He's sitting there at rest. We're going to look at him at kind of like a pendulum. So he's sitting there. He gets disturbed. Okay, he's in a medium. We said we needed a medium, but we also need something to disturb. We need a vibration. It needs to be disturbed. Okay, so he gets disturbed. He's going to travel that initial disturbance. Elasticity is going to take over. Remember, elasticity says, go back to where you came from. I didn't want to move in the first place. Now I'm going back. So he starts, elasticity takes over. So the molecule starts coming back, but now he's in motion. So what happens is inertia, okay, remember inertia wants to keep it in motion. Inertia takes over and says, hey, yeah, we're moving here, let's keep going. So they actually go back past the point where they started. They keep going. Let's stay in motion. Now elasticity takes over again. Whoops, I'm sorry. Elasticity takes over again and says, no, I want to go back to my point of rest. And it will bring it back to its point of rest. And if it were to stop there, we would have created one cycle, kind of leaping ahead a little bit. But let's say it didn't come back to rest, then it would keep going through because of an inertia again. Elasticity would take over, tell it to go back to its original, but then about this point inertia takes over because it's in motion now, and it says let's keep going, and then elasticity takes over and sends it back, and pretty soon we have our little guys, our little molecules bouncing back and back and back and back. And that little bounce, inertia, elasticity, and inertia and elasticity is called the simple harmonic motion of the medium. Okay, but now, like I said, we enter damping, and so friction, then if we didn't have friction, those little guys would just keep going boink, 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 boink all day long. But friction takes place. We have friction in mediums. It's inherent, and it finally brings it back to its point of rest. So it could be disturbed again. And the whole thing would happen again. So this is simply, so this is the motion of our molecules. Remember, they travel parallel to the direction of the wave, longitudinal wave. All right, well, for some reason, we like to look at this simple harmonic motion of our particles this way. We turn it so that this is now the y-axis and time becomes our x-axis. This is the same thing. This is our little molecule. So we have is here, this line represents, this point right there represents where that molecule was just sitting minding its own business. Then it was, a force was applied to it, was disturbed, it moved to its maximum excursion, then this is the point probably where elasticity took hold and it said, no, bring me back. But inertia takes over about here and says, wee, let's keep going. And then it happens again, and it brings it back, and it happens again and again and again and again and again and again. So I can't explain why we turn it on its side, but this, you can see, is simply this being plotted on an XY. This is Y and an XY graph. Okay, I'm going to stop there, and so this is what we just talked about. Then we'll call part 1 of the nature of sound.